In this video, I want to take a look at how tendons respond to mechanical loading, and I want to do so using our new favorite tool, the stress-strain diagram. So as a quick reminder, strain is this percentage change in length, and stress is mechanical force divided by the cross-sectional area. So what we're looking at here is what happens if you take maybe a tendon from a rat or something, or a cadaver, and then you start pulling on it like this. How, as a function of the force that you're pulling with divided by the cross-sectional area of the tendon, how does the tendon change as a function, how does the length of the tendon change as a function of this applied stress? So here's what happens. First off, let me pick up a better color. Let's use this. First off, you get this interesting phenomenon called a toe region, which I know we've mentioned before, and I'll explain now why that happens. You get this toe region. Then, like other materials, you have this linear region where the slope here tells you something about the stiffness of the tendon. And then eventually it will go like this, and then it'll either just snap immediately. And by the way, we have a name for that transition, right? We call that the plastic region often here. It'll either just snap immediately, or sometimes those little microfibers will start breaking and the tendon will elongate and then break, or just completely get stretched out like this. I'll show you a few real examples in a moment. For now, though, I want to take a look at this toe region and try to understand why tendon has this and for example, bone does not. So let's think about the structure of tendon. When it's relaxed, you have these nice wavy collagen fibers like this. And the explanation for where this toe region comes from is when you start pulling on a tendon, let's say it's secured over here, right when you start, you'll only be stretching out maybe just this one wavy collagen fiber. So here's the other collagen fibers, and then you stretch just this one out and it becomes taut. And then, because these collagen fibers are, by the way, they're sort of like bound to each other. They sort of like reach out and grab their neighbors. Once this one gets taut, then it's going to start pulling on this one. And so then you'll be pulling on two collagen fibers instead of just one. So then maybe the tendon stretches out a little more. The first one is getting taut, the second one's getting taut, and then you start pulling on the third one. And then the third one uncrimps and then starts pulling on the fourth one. So that is essentially why this is like the stiffness of one fiber, and then of two, and of three, and of four. And of course, really, inside a tendon, we're talking about thousands, not like four. But that's why you get this very distinctive toe region. It's because you could think of it like, imagine having multiple rubber bands that are of different lengths. So here you have a short rubber band, a medium rubber band, a long rubber band. If you started from a length of like here, this rubber band and this rubber band would be relaxed, right? They'd be just kind of hanging loose. And then once you started pulling on them a little bit more, then you'd start experiencing the tension of first two rubber bands and then all three of them. And you could imagine how that would give you this sort of ramp up in stiffness. Because again, remember, stiffness is roughly speaking that slope. So that toe region right here is a distinctive feature of tendons, and as we'll also see, ligaments and to some degree cartilage as well. When we talk about the stiffness of a tendon, we're usually talking about the slope in here. And in terms, and you don't need to memorize these numbers, but in terms of where we kind of operate in the body, generally this upper limit of safely stretching your tendon in the linear region, it's about maybe 6 to 8%. meaning the length of the tendon increases by 6 to 8%. So maybe if your tendon starts at 10 centimeters, it might stretch out to 10.6 centimeters. So that's a non-negligible stretch in, say, your Achilles tendon. But you want to stay within that area. Otherwise, of course, if you get up into here, the plastic region, what is happening at the microscopic structure, the reason you get this deviation from the linear trajectory is that those microscopic fibers start breaking. And that degrades the mechanical properties of the tendon. So this is the basics of mechanical loading in a tendon. And in the next video, I want to share an interesting phenomenon that we see in tendons called viscoelasticity.